Amy Garner. The parents of a baby from Barry who died on a flight home from a family holiday have spoken first to Real Radio.
We just want to say that we aren't blaming anybody. It's not about blame, or we're not bitter. You know, it's not going to bring our baby back, but we just want to be able to say this is deadly. MCAD is deadly if not detected.
8-month-old Sophia Williams stopped breathing on a plane home from the Canary Islands last September. Unknown to her mum Nicola speaking there, she had a genetic disorder known as MCAD, which proved fatal when she caught a stomach bug on holiday. Babies in Wales aren't tested for it at birth, despite it being a routine procedure across the border in England, something which Sophia's dad Dave says must change.
We're not out to blame anyone, but Wales should be screened as well as all the other countries. As an Englishman myself, that is why I'm a little bit bitter, because Sophia would have been born in England. She was 2 weeks early and she would have been screened in one of the Leeds hospitals.
Following yesterday's inquest into Sophia's death, a spokesperson from the Welsh Assembly government said work is underway to introduce screening tests for MCAD deficiency and sickle cell disease.
What is MCAD? Sorry, there we go. Come up busted. MCAD, it's acronym, you'll see it's spelled MCADD, and that is shorthand version for medium chain acyl-CoA dehydrogenase deficiency. It's a long name for a metabolic disorder. It basically means they can't break down fat from their bodies or their food for energy, so they have to eat every so often. At almost 18 months old, she can go 10 hours this time. MCAD, she cannot break down the medium chain fatty acids. There's a long, a medium, and a short. She can break down the long to get to the medium, but she can't break down the medium to get to the short. What happens when they go a long period without eating, either when they're a baby and they're sleeping, or at this age when they get sick with like a stomach bug or a virus, they get hypoglycemic, which can cause them to be lethargic and not want to eat even more. And then that can also lead to buildup of harmful material in their bodies, and which can cause seizures and comas and a lot of series of
This is a fascinating topic. I know I talked about it in the preview, but when we dive into this, you'll see that there are people who are around who have the inability to break down certain proteins. They have an inability to break down carbohydrates. And there are even those people who cannot live for an extended period of time without eating because they have an inability to break down certain fats and turn them into energy. It is a fascinating thing because it happens as early as birth, right? And so that's what the inborn part of these errors of metabolism. The inborn part is that it happens really early. The error part is that it has something to do with mutations, and mutations in genes, they matter. And we'll talk about those. And the metabolism part is that these early errors are affecting metabolism and affecting people's ability, or affecting individuals' abilities to break down carbohydrates, to break down fat, and to break down protein. Inborn errors of metabolism are single gene disorders, meaning that the disorder itself is caused by an individual mutant gene or mutation in one gene. So for every inborn error of metabolism, we can link it back to one gene where there is a mutation, and a mutation in that one gene leads to the disorder. The one gene normally leads to a misfolded or a dysfunctional protein. And we can see that that lines up with the central dogma. DNA is transcribed into RNA, which gets translated into protein. So some error in the DNA leads to a dysfunctional protein. And that is the case in what we're seeing in this particular set of diseases, these inborn errors of metabolism. We see something's wrong DNA-wise, and then something happens to the protein. So how do we define metabolism? Metabolism is a change, right? It's a set of life-sustaining chemical reactions in the organism. Metabolism consists of enzyme-catalyzed reactions. We have three basic purposes for metabolism. One, the conversion of food to energy, to run cellular processes. Two, the conversion of food or fuel as building blocks, or to build blocks of protein, to build lipid, to build nucleic acid, or to build carbohydrates. And then three, the elimination of metabolic waste. If we defined inborn errors of metabolism, it'll be defined as a group of congenital disorders caused by an inherited defect in a single specific enzyme that results in disruption or abnormality in a specific metabolic pathway. Broken down, so gene, messed up protein, messed up pathway. If you wanted to simplify that in any terms, there's something wrong with a gene. There's some mutation in the gene that leads to a dysfunctional protein, which leads to a disruption or abnormality in a specific metabolic pathway. All right, so as we break this down further, your inborn errors of metabolism is genetic disorders that affect the metabolism of food. So there are missing or defective enzymes necessary to metabolize food that we eat. What's in our food typically? Carbohydrates, lipids, proteins. That's what's in our food. And because that is what's in our food, those are the macromolecules that are in our food, we have to break those down. We normally break those down for energy. However, these inborn errors of metabolism, food is not broken down properly. That can lead to a buildup of chemicals in various parts of the body. That causes medical problems and learning disorders. And we'll see exactly what that's about before. I'll give you this example here, where you have a increase. So look over here, where you have A will typically break down into H. H is somehow turned into M and P. And don't forget the M, but we'll focus on the P initially. H is our substrate. Our substrate is typically, in most chemical reactions, your substrate is broken down into a product that is normally facilitated or catalyzed by an enzyme. The enzyme here is messed up. And why is the enzyme somehow messed up? Well, enzymes are proteins. Proteins are normally messed up because of multiple reasons, but one of those main reasons is because of a mutation in the DNA. If there's a mutation in the DNA, that leads to a dysfunctional or a absent protein. That problematic protein will affect this process. So what happens? Well, H can't get turned into P. So H, there's a buildup of H because H can't be converted to P, and there's a lack of P in this particular case, right? So accumulation and ablation. If we had to kind of look at it, accumulation and ablation. Accumulation is the buildup of something, and ablation is the deficiency in something. And so here you have an accumulation of H and a deficiency in P. And that's what we're going to see throughout, right? You can also possibly have an increase in M because H isn't being broken down into P, so you may have another buildup in M. What's the impact, right? What happens? What happens because of that buildup of H? And then what happens because of the deficiency of P? Archibald Garrod is the father of this whole inborn era of metabolism. His experiments in the 20th century led to us understanding inborn errors of metabolism. His work also contributed to this whole concept of one gene, one enzyme, further developed by Beadle and Tatum. And what does this mean? It means that when there's a gene, that one gene can actually have a product of one protein. And if there's ever a problem with one gene, then there's a problem with one protein. Or in this particular case, if there's a problem with one gene, there's a problem with one enzyme. And this follows the Mendelian inheritance concept. And so when he wrote his book, Gerard wrote a book about the inborn errors in metabolism. And this book kind of set the understanding of what this was all about. So I'll give you an example of what to look for in each one of these diseases. This is what I want to kind of talk about, just so you get it, and you have to understand this part. If you get this part, then you're ready to dive into any one of the inborn errors of metabolism, because this is how it breaks down. Here you have compound 1, and enzyme 1, and then compound 2. Your compound 1 will be your substrate. Your enzyme will be the enzyme or the protein that catalyzes this reaction, and then compound 2 will be the product. So substrate, enzyme, product. All right. Well, this enzyme is a protein. proteins, because of what we talked about when we discussed central dogma, this protein is the product of the DNA being transcribed in RNA and then being translated into a protein. If there's something wrong with the DNA, then there's something wrong with the enzyme. So this is how this typically works. The DNA is fine, the enzyme is perfect, compound 1 is converted into compound 2 by way of this enzyme and the catalytic properties of this enzyme. So this enzyme will catalyze compound 1 going into compound 2. However, in these cases of inborn errors of metabolism, then gene 1, there's something wrong with gene 1. In turn, there's something wrong with enzyme 1. So compound 1 cannot be turned into compound 2. Compound 1, what actually happens is there's an accumulation of compound 1. So there's a lot of compound 1s now. And what also happens is that there's a deficiency in compound 2. So accumulation, ablation. Accumulation, ablation. There's more of this, less of this because of a dysfunction with enzyme 1. And that will be a theme throughout the time when we look at these inborn errors of metabolism. So inborn errors of metabolism are impacted at 3 different levels. One, the gene level, gene mutation. The gene mutation leads us to an abnormal protein. Abnormal proteins are enzymes, are proteins, transport proteins are proteins, and of course, other proteins are proteins as well. Well, a dysfunction in the enzyme or the transport protein or other proteins lead to abnormal metabolites, either accumulation or ablation. Accumulation is the building up, and ablation is the deficiency in. So these gene mutations, SNPs, single nucleotide polymorphisms, abnormal proteins, either misfolded or deficient proteins, leads to a dysfunction in metabolism. So how do these pathways lead to disease? We talked about accumulation and we talked about ablation. Well, in accumulation, you have a accumulation of a substrate. So, for instance, our example of compound 1, piling up and piling up. Well, what's the consequence of having compound 1 pile up and accumulate and build up like that? There's a consequence to that, and we'll see that as a theme throughout our time talking about these inborn errors of metabolism. Well, the deficiency in the end product. If the end product is not there, what's the consequence of that? And that's where we have disease manifestation. In the accumulation, you have disease manifestation, and in the deficiency, you have disease manifestation. So as we dive into each particular inborn error of metabolism, I always want you to look for these few things. What's the gene that's leading to the protein? So what's the mutation in the gene? What is the protein? And then what is accumulating and what is deficient? So if you look for those things throughout, you'll have a framework in which to see each one of these inborn errors of metabolism. We'll talk about the enzyme. I will talk about the inborn errors of metabolism dealing with proteins. Then we'll talk about those dealing with carbohydrates, and then we'll talk about those dealing with fatty acids. All right, so now let's talk about the genetic characteristics or the mode of inheritance for these inborn errors of metabolism. Inborn errors of metabolism are autosomal recessive, meaning that you need 2 copies of a bad allele in order for you to get the inborn error of metabolism. That is very easy when you share a common ancestor, or when partners share a common ancestor. And yes, I'm referring to incest, and so children of incest will be highly susceptible to these inborn errors of metabolism, and you'll see that'll start to make sense to you while we're diving into some of the consequences of inborn errors of metabolism. There are some that are X-linked recessive and others that are autosomal dominant, but for the most part, the inborn errors of metabolism are autosomal recessive. As we go through, we'll first talk about the proteins, or the protein related inborn errors of metabolism, then the carbohydrate inborn errors of metabolism, and finally the triglyceride errors, inborn errors of metabolism. So the first inborn error of metabolism we'll talk about is PKU.
PKU is where you're born without or lacking an enzyme, pH enzyme, that breaks down phenylalanine, which is one of 20 amino acids in a protein. So in general, I just can't eat a lot of protein. And there's a lot of restrictions, and there's dietary formulas I have to drink to get the proper nutrition in my diet that I don't get otherwise. It's mainly important for the different time ranges that you would go off your diet. So whenever your brain is developing, that's when you're most vulnerable to having bad effects happen. So if you had a lot of protein, there's the blood-brain barrier, and the phenylalanine that I can't break down because of my enzyme, it builds up in my bloodstream, and when it crosses there, it causes havoc in my brain, especially I think the frontal lobe. So a lot of organizational skills, various other things. That attention deficit disorder seems to be a common theme for a lot of people who have this disorder.
The very common inborn error of metabolism, and when I say common, I mean that it's one that people generally talk about. The first one they think about when you bring up inborn errors of metabolism. It's not ridiculously common in the U.S., but 1 in every 15,000 people are born with PKU. It's a greater incidence in Caucasians and Native Americans, but less in African Americans. Essentially, you see a delay in infancy, neurological manifestations such as seizures, hyperactivity, behavior disturbances, hypopigmentation, and mental impairment. Most of the manifestations of the clinical features are related to how this comes about. So in PKU, the enzyme phenylalanine hydroxylase will add a hydroxyl group to phenylalanine to convert it to tyrosine. Whenever the phenylalanine hydroxylase enzyme is dysfunctional, then you'll have a buildup of phenylalanine and a decrease or a deficiency in tyrosine. So the accumulation is the phenylalanine, the ablation is tyrosine. And in this particular case, phenylalanine is very important. It's involved in making neurotransmitters and hormones. However, tyrosine is also important, and while tyrosine is involved in skin and melanin. And so whenever you don't have tyrosine, then you'll see clinical features like hypopigmentation. However, when you have a accumulation of phenylalanine or you don't have the proper metabolism of phenylalanine, then you see the neurological manifestations such as seizures. Diagnostic, and this will be across the board, when we talk about these diseases, the diagnostic normally happens during your newborn screening. And so they look for levels of phenylalanine in the serum, and they look for it the second or third day after birth, right? So phenylalanine levels are normal at birth, but 2 or 3 days later, they want to look for how much phenylalanine is there. If you have elevated levels of phenylalanine, then they normally say, this patient has PKU. So how do I treat this? Well, dietary reduction of phenylalanine within the first 4 weeks is key in making sure you have a better prognosis. This is the pathway, the metabolic pathway for this amino acid disorder. Through your diet, you'll get your phenylalanine. Phenylalanine is normally converted into tyrosine. However, if you have a dysfunctional phenylalanine hydroxylase or a deficient phenylalanine hydroxylase, then that conversion from phenylalanine to tyrosine is not there. Well, the conversion from phenylalanine to tyrosine is important because you need tyrosine. Tyrosine is involved in all these other processes that lead to proper pigment. So if you look down the arrows from tyrosine, the arrows lead all the way to pigment. Well, if you don't have enough tyrosine, then you have a problem with pigmentation. The accumulation of phenylalanine leads to neurological disorders.
William is my 17-year-old big brother, and he's loud and sings a lot. William's got a disease called citrullinemia, which is where protein in your body doesn't break down properly, which causes his blood to get a poison in it. And when this poison builds up, it makes him vomit or have seizures. So we have to take him into hospital, which I suppose is a bit different from other people's lives. And other things that he's got since he's been born are brain damage and ADHD and ODD, but I'm not really sure what that one is. On a day-to-day basis, William can change his mood several times. He can wake up in the morning being angry about going to school, and then by lunchtime he can be singing and dancing around the house, but it's how it's always been.
When did you find out William had citrullinemia?
It was when he was just 3 days old, and we were really lucky because a doctor down at our local hospital had seen it before. It's so rare that often it's not picked up, but she had seen it, and we were very quickly transferred to London. I didn't know anything about citrullinemia, but I knew that there were a group of diseases called metabolic diseases, as a friend had one. So I almost knew a little bit too much about that, but I didn't realise how many sorts there were.
How did you feel when you found out William had citrullinemia?
Well, it was strange because it was sort of a disbelief, but I was glad to be listened to because I knew something was wrong that morning. And it's a bit like a grieving process because you grieve for what you might have had, but then you start to learn to live with the disease, and then you forget the disease and you think about the person.
All right, so the next inborn error of metabolism we'll talk about is citrullinemia. It is a urea cycle disorder, and it has a lot to do with not the inability to eliminate toxins or toxic ammonia from the body. And this is normally caused because of a gene AAS1, and mutations in that gene leading to your inability to break down certain parts of the urea cycle. So what you see here is excessive levels of ammonia and excessive levels of citrulline in the blood strongly suggest that you have citrullinemia.
A normal day consists of about 5 sets of medicines, which if he didn't have, his body wouldn't be able to function.
Although he's 17, we have to remember that he's more like 6 because of his disease. So you have to think of things that he might like to do even though he's 17 that are a bit younger, and he has to travel with his medicines. If he goes on holiday, you have to let the nearest hospital know that he's there, and it's things like that. And if he goes somewhere where he's going to eat, you have to measure the protein.
Prompt treatment is necessary. There are certain medications that are used to remove excess nitrogen from the body, and so you want to get rid of toxic ammonia from the body. Well, you have to remove the nitrogen from the body, and you can do that through several different medicines, but you have to diagnose that pretty early. All right, so here's an example of what I mean. So you see the dysfunction in ASS1 will lead to a problem with converting citrulline into arginine acid. And the inability to do that will lead to an accumulation of citrulline. The accumulation of citrulline will have its own symptoms involved. So you'll see symptoms like lethargy, irritability. You can see coma as see coma as well. The treatment for this is a low protein diet. The low protein diet, because you want to avoid having to break down certain amino acids. And you want to avoid having to break down citrulline, and citrulline can be found in your high proteins. Next, I've talked about the maple syrup urine disease, which has a very funny name for some people. You see maple syrup and you're like, okay, why is this called the maple syrup urine disease? Well, it's called the maple syrup urine disease because of its characteristic where you have a very sweet smelling urine, more like maple syrup or burnt sugar odor, which is a main clinical feature of the maple syrup urine disease. The reason it's caused is because of an inability to break down branch chain amino acids. So your inability to break down branch chain amino acids like leucine or isoleucine or valine are the main reasons for this disorder. So the treatment for this is to avoid foods that contain these branch chain amino acids. And you can also treat with a supplementation of thiamine, and you can also get a liver transplant. The genes that are typically affected here are BCKDHA, and then BCKDHB, and DBT genes. And so all of these genes are involved in this maple syrup urine disease. what you'll see here in the maple syrup urine disease is a buildup of leucine, so buildup of your branch-chain amino acids, because of the inability to break those down. Those are typically broken down by a branch-chain keto acid dehydrogenase complex. So the BCKD, the BCKDC, or the branch-chain keto acid dehydrogenase complex, breaks down leucine, isoleucine, valine, once they're broken down into these alpha keto acids. And so an accumulation of alpha keto acid is a telltale sign that you'll have maple syrup urine disease. An accumulation of leucine, isoleucine, and valine is also seen whenever there's a maple syrup urine disease. Now let's talk about the carbohydrates, and there are certain inborn errors of metabolism strictly dealing with carbohydrates. So carbohydrates typically break down into glucose. Glucose through the process of glycolysis will give us pyruvate, acetyl-CoA, and then through the Krebs cycle we'll get to energy. And so the consequence of a lot of these inborn errors of metabolism as it relates to carbohydrates would be a decrease in ATP, right? And we'll look at that across the board and see exactly what are some of the other consequences involved in these inborn errors of metabolism as it relates to carbohydrates. So carbohydrates are natural compounds, carbon, hydrogen, oxygen, that serve as the body's primary energy source. They can be divided into simple carbohydrates, which include monosaccharides, disaccharides, complex carbs, and polysaccharides. And so, for examples of monosaccharides, it's glucose and fructose and galactose. For examples of disaccharides, it's your table sugar, sucrose, and lactose found in milk. The complex carbohydrates are starch, and then your polysaccharides or your non-starch polysaccharides are, for polysaccharides, glycogen, and then for your non-starch polysaccharides, cellulose, which can be found in plants. And so that's why, if you ever look at the back label of spinach, you may not expect to see, carbohydrates in there, but there are carbohydrates in there, and you'll see them with 3 grams of carbs normally because of cellulose. Now, your monosaccharides are typically absorbed directly into those intestinal cells, right? However, your disaccharides and polysaccharides have to be broken down into monosaccharides, and that's where we have some of our issues when we'll talk about this disorder. There's also issues with breaking down just the monosaccharides, right? However, we'll see that there are multiple areas where there's a mutation in a gene, which will lead to a dysfunctional or a ablated protein. So the inborn errors of carbohydrate metabolism that we'll talk about is one is glycosemia. And there are 3 different types of glycosemia, and we'll talk about that. The other one is hereditary fructose intolerance.
I want to pick up red one right there.
Joey Tanella is a typical 8-year-old boy having fun with his parents and sister.
I like to do homework, eat lunch, and snack.
He's among the millions of people in the U.S. living with a rare disease diagnosed at just 2 days old.
The doctor called me and they said we have to immediately bring Joey to the hospital. We had to immediately stop feeding him. During those days, his organs were failing. Essentially, his liver was failing.
Joey has galactosemia, which occurs in about 1 in 50,000 births. The rare genetic metabolic disorder is life-threatening because it affects the body's ability to process a sugar called galactose. The only treatment is to avoid foods that contain galactose or lactose found in all dairy products.
We believe that most of the babies that are not recognized in the newborn period don't survive.
All babies in the U.S. are now screened for galactosemia, but Dr. Jared Berry at Boston Children's Hospital says even with early diagnosis and a restricted diet, patients can still suffer speech and motor skill delays and learning problems.
The goal of all of our research now is to try to understand what causes this and how we can improve the lives of these patients.
There are about 7,000 rare diseases in the U.S., and many of them, like galactosemia, have no FDA-approved treatments. That's something that researchers and families are hoping will change with more awareness and funding.
He does have developmental delays associated, primarily being speech.
The Tanellas say Joey's rare disease is just a part of who he is.
Joey is a hard worker. He loves running. He's very athletic. he doesn't give up, and I think he actually made both of us better people.
We want him to have the best possible life that he can, and he's having that right now.
So your galactosemias are galactose kinase deficiency and classic galactosemia. And then the other one, the not so severe urine diphosphate galactose 4 epimerase deficiency. So when we talk about the first two, which is your galactose kinase deficiency and then classic galactosemia, the incidence for actually all of these are 1 in every 16,000 live births. And you can see an impact in both male and female. The onset is typically infancy. These are autosomal recessive disorders, as in most inborn errors of metabolism. The enzyme impacted for galactose kinase deficiency is galactose kinase. And the enzyme impacted for classic galactosemia is galactose 1 phosphate uridyl transferase. The galactose kinase deficiency, or some people call it type 2, is rare. It's not common. However, the frequency for classic galactosemia is a lot more common. What happens in galactosemia kinase is a conversion from galactose to galactose 1 phosphate. Kinases generally give phosphate groups or add phosphate groups to compounds. And so in this particular case, your kinase is not functional and unable to convert galactose into galactose 1 phosphate. For galactosemia, you have a galactose 1 phosphate, which typically gets converted into UDP galactose. However, that's unable to happen because of a malfunctioning galactose 1 phosphate uridyl transferase. The severity for the galactose kinase deficiency is mild. However, for classic galactosemia, it's quite severe. And for the other one, for uridine diphosphate galactose 4 epimerase deficiency, it's typically asymptomatic. However, you can experience jaundice or failure to thrive or cataracts. Now, for galactose kinase deficiency or type 2, you're going to see cataracts most likely because of an accumulation of galactose. Accumulation of that galactose or that monosaccharide can lead to cataracts. In classic galactosemia, you see poor feeding, failure to thrive, vomiting, diarrhea, cataracts, and cognitive impairment. Where can we diagnose this? This stuff is normally diagnosed around the newborn screening. The newborn screening is so important. It comes up in all of these. And what you're looking for is increased levels of galactose. Increased levels of galactose, that's the accumulation here, will show in those tests. And then is on to the treatment, which is to get rid of all lactose containing feeds and a lifelong adherence to staying away from galactose and lactose. The next inborn error of metabolism we'll talk about is hereditary fructose intolerance. In that case, you have clinical features like bloating and sweating and vomiting, failure to thrive, jaundice, bleeding tendencies. This happens in 1 in every 18,000 live births, normally of European ancestry. The problem here, a defect in aldolase B, which typically converts fructose 1 phosphate into glyceraldehyde and dihydroxyacetone phosphate. Treatment, a lifelong adherence to fructose-free or artificial sweetener-free lifestyle is necessary. Finally, we'll talk about the ingested triglycerides. All right, so we've talked about protein and some of the inborn errors of metabolism involved in protein. There are inborn errors of metabolism that strictly involves carbohydrates. But now, finally, let's talk about the fat. And what are some of those inborn errors? What is the major inborn error of metabolism as it relates to fat? And this is a very interesting one to me. So fatty acid metabolism, let's just kind of look at it as an overview. Fatty acid or triacylglycerides are important energy carriers. They are stored in your adipose tissue and can be metabolized for ATP production. What does that mean? Well, typically we first break down our carbohydrates, then we break down our carbohydrate stores like glycogen, and then we start dipping into the fat, right? What do you mean? That means that if you starve for an extended period of time, your body starts breaking down fat for energy. Simple, right? Well, because your body breaks down fat for energy, what do we do? So they start to break down these triacylglycerides. Your triacylglycerides are a storage form for fatty acid in the body. So it consists of one molecule of the glycerine esterified with 3 fatty acids. And so you'll see this whenever people talk about saturated fats versus unsaturated fats. So what are saturated fats and unsaturated fats? We'll talk about that in just a second. But whenever people talk about that, you see a normal triacylglycerol structure, because it's very clear to show the difference between saturated fats versus unsaturated fats whenever you're showing those fatty acid chains. A main goal of breakdown of fatty acids is energy. This happens in the mitochondria and involves your liver, adipose tissue, and muscle. What's required to break down fat? Well, NAD+ is required, FAD is required, and water. So if you ever wondered why people who drink a lot of water are people who are losing a lot of weight or drinking a lot of water, water is required to break down fat. So the end product here is acetyl-CoA, ketone bodies, NADH+, FADH2. And let's talk for a second about ketones. So as you break down your fat, your preferred source of energy is glucose, right? Your body wants glucose. However, when you burn through the glucose, your brain will accept ketones. And so when people are on keto diets, normally what you'll see is if you really want to know if you're in a state of ketosis, you go to a store, you buy some keto sticks, and you pee on the stick, and you're hoping to pee purple. And what do I mean by pee purple? You're hoping that when you pee on the stick that it turns purple, which is an indication that you have ketones in your urine. An indication of ketone or seeing ketones in your urine means that you have now converted, or your body has converted from using glucose as the main source of energy to breaking down and using fat as a source of energy. And so people who are on keto diets are really looking to pee purple, and that's one of the things. So when you know you're using are breaking down fat into energy, you should be producing ketones. And if you do it enough, you'll have those ketones in your urine. So fatty acid characteristics. So the fatty acid chain length, so we'll talk about those. The short chain fatty acids, which is about 1 to 6 carbon chain length. Medium chain fatty acids are between 7 and 16 carbons. Your long chain fatty acids are between 13 and 20 carbons. Then you have very long chain fatty acids, and then odd chain fatty acids. So in these typical cases, you see how it ends between 6 and 12 and then 20. But your odd chain fatty acids will contain odd numbers of carbon atoms. We talked about this earlier, but this fatty acid saturation. So how do you know you have a saturated fat versus an unsaturated fat? Saturated fats have long chains of these carbons and no double bonds. Unsaturated fats have long chains of carbons, but they have double bonds. And so those double bonds are a little bit more, and I always say, look a little bit more kinky, right? But your saturated fats have no double bonds, and the unsaturated fats have double bonds.
We did it, and thank God we did, because that tiny little heel prick helped us to get an early diagnosis on our child that helped save his life. He was born, and when he was born, he didn't cry, anything like that, and he had very, very low blood sugar. So kids with MCAD cannot convert stored fat to energy. Specifically, medium chain fats cause a big issue with them, things like avocados and coconuts. But when he was first born, he was given this little bottle of sugar water, which inevitably saved his life at the time, and we didn't know it. Needless to say, it's a disorder that we had never heard about. It's a disorder that even a lot of local pediatricians had never heard about.
In fact, only one.
One did. And by the pure grace of God, it's the one that we said, yeah, we want to use that doctor. She showed up and she had had one other case in her entire career. The poor kid was in and out of hospitals, getting pricked, tests, all sorts of things, probably 4 times in the first month of life, in addition to urine samples, different honestly, like genetic threads were being ripped apart on these studies just to ensure that he did or did not have it. Because if he was diagnosed with it, it meant that we would have a pretty rigid feeding schedule for his first few years of life. So what that ended up looking like was, yes, we went to OU Children's Hospital. We got the diagnosis that he did confirm positive for having MCAD. And while we got that, and it was scary, we were kind of relieved to know that there was a treatment path in place so it could be managed throughout the course of his actual little life into adulthood to live a full, thriving, happy, healthy life. What that looked like for us, though, was feeding around the clock every 2 hours until further notice. And then it hit his first rotavirus case. And we were like, well, rotavirus isn't even MCAD related, we'll be fine. The thing with MCAD is, think about it like a car. If you have a leak in your, what it would be, a gas?
Your fuel tank.
Your fuel, I was gonna say your gas can. A leak in your fuel tank, eventually your car is just gonna stop. And kids with MCAD, when that fuel tank runs out, which would be like our fat reserves, he can't pull from his fat reserves. So the only thing that works is food keeping him fueled. And then he has to take a special medicine to flush out the excess fats. Well, when they're sick, either things are coming out the attic or the basement, for lack of better terms.
The attic or the basement. Wow.
Basically, when that happens, they go into almost a internal catabolic state where things start to shut down and feed off of themselves. And it can be fatal. So if we don't get him immediately to a hospital to get a special kind of IV drip, he could potentially pass.
So let's talk about this final inborn error of metabolism that we'll discuss, which is MCAD. MCAD is a medium chain acyl CoA dehydrogenase deficiency. And so a deficiency in MCAD means that you do not have the ability to break down your fat as a source of energy. That's the breakdown of it, for real. Like, that's kind of how you look at it. So most people who have MCAD deficiencies can't go on extended bouts of fasting. And so you have, some people go into intermittent fasting for weight loss. Well, these people who suffer from MCAD deficiency cannot do that. They cannot afford to go for long stretches of time without food. And so, because they can't, after they break down their carbohydrates, after you go into your glycogen stores, you can't start dipping into your fat in order to pull a new source of energy. And you see this at the very onset of life. And so this is the major reason for, for a major reason for crib death, right? So babies are sleeping throughout the night. They're not being fed. And as they're not being fed, then they can pass away. Like, that is definitely something that can happen when you see an MCAD deficiency. And I'll kind of break that down a little bit more. In the first few years, most commonly, if you don't get all that far, you see dehydration, poor feeding, vomiting, lethargy, seizures. Some people can dip into a coma, or hypotonia. This occurs in about 5 in every 1,000 births. It's common among Northern Europeans. And the gene that's associated here is ACAMD. Remember that. We'll talk about that in a second. So this is a part of the newborn screening as well. This is a very important part of the newborn screening, because not understanding what's going on here matters, right? It'll really matter when it comes to infant mortality. So how do you treat this? Well, normally it's a IV administration of about 10% dextrose during acute decompensation. So if you have a baby who needs to be on, because babies are typically sleeping a lot, right? They need to be on a constant source of carbohydrates. So your diet is high in carbohydrates and very low in fat, because you don't have the ability to break down fats as well, and you avoid fasting states. And so feeding is key and necessary. Typically, through the diet, we ingest these triglycerides, break those down into long-chain fatty acids, long-chain acetyl-CoA, then long-chain acetyl carnate, and then long-chain acetyl CoA from there. Then from there, once we get into the inner mitochondrial membrane, long chain fatty acid acyl CoA, and then medium chain fatty acid acyl CoA, which helps us then break down into short chain fatty acid acyl CoA. However, your inability to break down medium chain fatty acid acyl CoA means that you're going to have a decreased amount of acetyl CoA, and a decreased amount of acetyl CoA means that you'll have a decreased amount of ketones. So your brain likes to switch off as an energy source to ketones whenever there's not a lot of glucose around. Well, you're not making a lot of ketones. And because you have this inability to break down these medium chain fatty acids, the inability there means that you have a decreased amount of ketones, and you can go into a coma because you don't have an energy source for your brain. So these extended periods of fasting for people who deal with MCAD is not a thing. So MCAD is caused by a mutation. It's a point mutation where an adenine is replaced by a guanine at position 985 in the coding region of the gene. What happens is, in the protein is an amino acid switch from lysine to glutamate at position 304. As I'm putting together this video, I'm looking at multiple cases of, examples of families being impacted by these diseases. However, I'm looking for African American family that was impacted by MCAD, and I couldn't find one. And I was looking for why. So this paper kind of illuminated that for me. What they did was they looked at 1.1 million newborns looking for this point mutation, this 985 A to G point mutation, and specifically looking for babies that were homozygous for that mutation. Of the 1.1 million newborns that they looked at, no Asian or Black homozygotes were identified. Not one. And that explained to me why I could not find any African American families who were on, YouTube sharing their MCAD story. So I'm not saying it's not possible, it's just that it's very rare. So hopefully you got a chance to, really dive into that content. The inborn errors of metabolism are very, very interesting. There are more, some dealing with cholesterol, and some dealing in other places. So what I want you to do is dive into this week's paper, really enjoy this content. These inborn errors of metabolism are fascinating, and hopefully you get a chance to fully understand it, and I hope you get it. If you have any questions, any questions around this content, you want to ask me anything, please feel free to reach out to me, and we can talk more about these inborn errors of metabolism. All right, have a great day.